Welcome back to the deep dive.
And today, we are tackling a concept that is, well, it's moving incredibly fast from this sort of niche academic thing to being the absolute center of the quest for superintelligence.
We are talking about the value function.
It sounds dry, doesn't it? It sounds like something you'd pull out of a control theory textbook or some dense mathematical paper.
Right.
But in the world of advanced AI, it is anything but dry. I mean, you could almost say it's the operating system of wisdom itself.
And wisdom, as we're about to find out, is the one thing current AI just fundamentally lacks. Which brings us to this kind of paradox we want to start with today.
Go on.
What exactly is the value function when we're talking about AGI? I mean, are we in our rush to build superintelligence? Are we sort of like trying to build a massive hydroelectric dam on a river that's just fast and twisting and completely untamed?
That's a great analogy. It really hits the mark because we have this immense energy, right? The compute, the data, all the parameters, the power is there.
Unquestionably.
But what we've been missing up until now is the regulatory mechanism to actually channel that power, to guide it towards outcomes that are not just plausible, but reliable and trustworthy.
Well, the value function is the dam.
The value function is the dam. It's the guide rails. It is that crucial self-imposed constraint that turns raw power into productive work.
And here's the thing that really unpacks why this matters so much. It's not just about machines. This whole endeavor, this pursuit of superintelligence that people like Ilya Sutskever are leading, it's forcing us to look in the mirror. It's forcing us to confront the very core of our own evolutionary wisdom. What actually makes humans successful, it's not just that we can calculate faster. It's our ability to stop, to reason, to question our own gut impulses.
We've spent, millennia evolving these incredible mechanisms for filtering signal from all the noise out there, for distilling actual knowledge from just this ocean of raw information.
A human chess master doesn't win by checking every single possible move.
No, absolutely not. They win because they have this innate wisdom, this trained intuition to just discard a billion bad ideas in an instant without even thinking about them, that judgment. That's what we're now trying to distill into an algorithm.
And so this whole technical journey, trying to define the algorithmic core of judgment for an AI, it paradoxically forces us to get really clear about our own minds.
Yes.
What even is knowledge, fundamentally? And maybe even more profoundly, how do we define what work really means? What does it mean to work effectively towards a goal when you're in a universe that is just, by its nature, ambiguous and noisy?
That distinction right there, knowledge versus raw, chaotic information and effective, low entropy work versus just wasted high entropy energy. That is the philosophical bedrock of all the research into the value function. It's trying to chart a direct, explicit path from what is just pattern matching computation to what we could call genuine self-correcting cognition.
I'm Satosha.
And I'm Satoshi.
Okay, so let's unpack where all this urgency is coming from, because this isn't just a theoretical deep dive for us. The catalyst was an interview that's been making the rounds in the AI community.
The one with Gorkesh Patel.
Exactly. Dorkesh Patel interviewing Ilya Sutskever, who co-founded OpenAI and is now leading Safe Superintelligence, Inc. And, Sutskever is basically betting his entire career and maybe the future of the whole field on this one concept.
And what was so striking, what resonated with both of us, was just the conviction in his voice. He basically declared that the old era, the era of just scaling models up, making them bigger, feeding them more data, is over.
It's hitting a wall.
It's hitting a wall. And he said the next big leap isn't about size anymore. It's about architecture. It's about reasoning. And the value function is the engine that drives that reasoning.
And when you hear that from the person who literally built the most successful large language models in history, well, that sent us down a pretty serious rabbit hole.
A very deep one.
So our mission for this deep dive became, how do we articulate this idea, the value function, for you, for someone who hasn't been buried in the literature, and do it in a way that connects it not just to the technical math, but to, information theory, and maybe even that bigger, almost spiritual quest for truth.
The goal was really to chart that path, to show how you get from brute force computation to something that is verifiable and reliable, something like cognition. We wanted to fully grasp what Sutskever meant when he called the value function the AI's internalized judgment.
It's gut check.
It's gut check. It's internal measure of confidence. Exactly.
And full disclosure here, because this concept is so fundamental, we actually spent days doing the primary research. And don't worry, we won't be reading equations.
No calculus today.
No calculus. But we did formulate some of the core math ourselves, just to make sure we understood it from the ground up, to really hit a deeper accord with the reality of it, to link the physics of entropy to the philosophy of knowledge.
It's the only way to really appreciate that this isn't just some small tweak. This is a complete architectural overhaul. It's about moving AI from being a sophisticated statistician to a genuine thinker.
We'll put a link to the original video with Ilya and to our own paper that explains the concepts in the description. So feel free to check that out if you really want to see the underlying geometry of these ideas.
It's pretty fascinating stuff.
But before we dive into the scaling wall, we just have to take a moment. The response from this community has been just phenomenal. You are all sharing, critiquing, challenging us. You're driving this research forward with us.
So thank you. Thank you for being such sharp, dedicated listeners. It really means a lot.
And speaking of dedication, we are truly committed to making videos of this content. Not just screen recordings, but beautiful, creative, immersive, visual deep dives that really enhance the learning experience. Our dev team has found what they think is the holy grail for this.
The Mosaic AI video editor, they're calling it.
Exactly. It's a powerful system, but it's a huge investment. And in order to unlock the funding for Mosaic, we need to hit a milestone. We need to get to 1,000 subscribers combined across all the platforms we're on.
So that's YouTube Music, Spotify, Apple Podcasts, Fountain, basically wherever you can get podcasts that are compliant with the podcast index.
So please, if you value this content, if you want to see it brought to life in a really thoughtful video format, just take a second and hit subscribe wherever you listen. It would help us a ton.
It really would. Okay, so now, let's get into it. Let's talk about the end of an era.
Let's do it. We have to start with where AI is right now. What Sutskever and others are basically calling the twilight of the scaling era.
Yeah.
For the last, decade? The huge improvements we've seen, the things that gave us GPT-3 and DALL-E, they were all driven by one core belief.
The scaling hypothesis.
The scaling hypothesis.
And the hypothesis itself was just, it was delightfully simple and for a long time devastatingly effective.
Which was?
It was that if you just systematically increase three things, compute, so processing power, data, the size of your training corpus, and parameters, the model's internal complexity, you would get predictable, reliable improvements in performance.
Bigger is better.
Yeah.
And you could plot it on a graph.
You could plot it, a power law curve. And that formula, I mean, it delivered. It gave us the encyclopedic LLMs we all use today, these systems with just a staggering breadth of knowledge.
But now that whole paradigm is confronting a fundamental constraint, which you called the scaling wall.
Right. And it's really two walls. First, there's the data wall. High-quality data is finite. I mean, we are rapidly running out of unique, curated text on the internet to feed these things. You can't just keep scraping forever.
We're eating our own tail at some point.
Exactly. And second, there's the economic and, frankly, the physical wall. You can't just keep quadrupling the size of these models forever. The energy costs, the financial costs, it's just not sustainable. We have to find a way to be more efficient.
So we're moving from this age of scaling, where you could guarantee success with just brute force, into an age of reasoning, an age of architectural research.
And as soon as you make that shift, the inherent flaw in the current models becomes painfully obvious.
Which is their inconsistency.
It's their inconsistency. The flaw is structural. People describe current models as jagged.
Jagged.
1 minute, it can write a perfect sonnet. The next, it can prove some complex mathematical theorem. But then you ask it a simple logic puzzle, and it fails spectacularly. Or it hallucinates a fact with 100% confidence.
So why? Why that inconsistency?
Because they operate almost exclusively as what psychologists would call System 1 thinkers.
Right, from Daniel Kahneman's work. System 1 is the fast, intuitive, automatic thinking. It's what lets you drive a car or recognize a friend's face without any conscious effort.
Precisely. Current LLMs are trained for one thing above all else: speed and fluency. Their entire objective function is to maximize the probability of the next token. They are, at their core, incredibly sophisticated autocomplete machines.
They're feed forward. They just go in one direction.
One direction. They lack any internal mechanism that's analogous to human system 2 thinking, which is our slow, deliberate, critical, self-correcting mode.
They can't pause. They can't evaluate the quality of what they've already written and then decide to replan their output. There's no internal critic, no self-doubt.
None at all. Which brings us to an analogy that I think really crystallizes this entire deficiency. We call it the genius intern analogy.
Okay, let's hear it.
Imagine you hire a new intern. This intern is a true prodigy. They have, like, perfect memory, access to the entire Library of Congress, all of human history, philosophy, engineering. That's the pre-training data.
So massive raw intelligence, massive processing power.
Off the charts. Now, you give this prodigy a really complex, ambiguous, real-world task. Something that isn't in a textbook, something that requires navigating, say, a delicate social situation or a novel ethical trade-off.
Oh.
They would almost certainly fail, catastrophically. They can quote Sun Tzu's Art of War from memory, but they have no idea when to apply one of his maxims during a high-stakes, real-time negotiation.
So they have the knowledge, but not the wisdom.
They have encyclopedic knowledge, but they lack judgment. They can execute on facts, but they cannot evaluate the value of those facts in a new, ambiguous context.
And the LLM is this intern.
The LLM is this intern, all the raw intelligence, all the processing power, but it's missing that internalized heuristic framework, that accumulated wisdom of what works, what doesn't, and most importantly, what is safe.
So that framework, that is the value function.
That is the value function. Sutskever's whole argument is that true, reliable competence and the eventual emergence of AGI will only happen when the agent can internalize this judgment. It provides the gut check. It's what upgrades the AI from a simple, impulsive text generator system 1 into a self-aware, robust agent that can actually guide its own search for truth. System 2.
So it's the thing that elevates the LLM from being just a generator of plausible-sounding text to a genuine solver of problems.
It's the difference between knowing all the rules of chess and having the instinct, the deep understanding of which moves are likely to lead to a good board position down the line. It's about projecting value into the future, not just predicting the next word.
Okay, so if the value function's judgment, how on earth do we install that into a neural network? Let's get a bit more precise. We've said it's judgment, but what is it, technically?
Technically, it's a mechanism that assigns a scalar value, just a simple number, like 0.1 for bad, 0.9 for good, to a specific state or a specific step in a chain of reasoning.
A numerical score for correctness at each point.
Exactly. And to implement that, you have to make a huge architectural shift away from the way we currently train these models, which is a paradigm called outcome supervision.
Right. And let's be really clear on why outcome supervision has failed to create this kind of judgment.
Okay, so in this setup, the model is judged purely on the final result. The model generates an entire piece of work. Let's say it's a 200-line piece of code or a multi-step mathematical proof.
And it only gets feedback at the very end.
Only at the very end. A single, sparse reward signal. Did the code compile and run correctly? Yes or no? Did the proof arrive at the right answer? Pass or fail?
And if the final product is perfect, it gets a +1. If it's flawed, it gets a -1. And this is where we run straight into this massive challenge called the credit assignment problem.
A colossal challenge. Imagine the AI writes that 200-line piece of code. It fails. That single -1 reward signal gets applied to the entire 200-line output.
So the model has no idea where it went wrong.
It has no clue. Was the mistake a tiny syntax error on line 5? Or was it a fundamental catastrophic logic error in the core algorithm on line 195? The model can't tell.
The signal is too sparse. It's too far away from the actual mistake.
Exactly. And because this flawed system only rewards the final outcome, it ends up rewarding brittleness and mimicry. If the model gets the right answer through a flawed but lucky process, a kind of lucky guess, it gets rewarded.
So it learns to just mimic the appearance of truth.
It learns to mimic the superficial patterns of successful outputs rather than mastering the actual invariant process of deriving truth. And that's how you get the stochastic parrot, perfect fluency, but no real understanding.
So the solution that Sutskever and others are pushing for is this shift to process supervision. And this is where process reward models, or PRMs, come in.
The PRM is the direct technical implementation of the value function we're talking about. Instead of that one single sparse reward at the end, the PRM provides a dense signal.
Dense meaning continuous.
It means it scores every single step of the chain of thought right after that step is taken.
So, if the AI is writing a mathematical proof, the PRM is evaluating the logical soundness of line 1, then the validity of the inference in line 2, and so on.
Precisely. It's explicitly telling the AI, step 5, that's a perfect application of the theorem, high value. And then step 6, that's a complete non sequitur, low value. It solves the credit assignment problem instantly because it localizes the error.
And that forces the model to learn the actual rules of the game.
It forces the model to learn the fundamental invariance of correct reasoning, the actual structure of a valid argument, not just what a final correct answer looks like.
Okay, but I can hear someone listening to this and thinking, hold on, that sounds incredibly expensive. I mean, you're saying human annotators now have to label not just the final answer, but every single logical step in a long chain of reasoning. How does that even scale?
And that is the absolute core difficulty. Collecting the data for PRMs is expensive, it is slow, and it requires highly skilled human experts to create that ground truth data of what a correct reasoning process looks like.
But the payoff is worth it.
The payoff is revolutionary. As they showed in this seminal research paper, let's verify step by step, which Sutskever co-authored. And it leads to this truly breakthrough finding they called the negative alignment tax.
Okay, let's pause on this because this idea is really powerful. For years, the whole field of AI safety or alignment was seen as a tax, a cost.
A performance cost, yeah.
Yeah.
The idea was if you want to make an AI safe, you have to put constraints on it. You have to, muzzle its capabilities, which would naturally make it worse at solving hard problems.
Safety came at the expense of capability.
That was the accepted and very pessimistic worldview. But this paper showed the exact opposite. Process supervision creates a negative alignment tax.
Okay, explain the mechanism. How does forcing an AI to be honest actually make it smarter?
So when you train the model with these PRMs, what you're rewarding is logical integrity, verifiable steps. That's the definition of alignment, really. You're teaching it to be honest about its own thought process. What the research showed was that by training the model to be honest and verifiable in this way, you dramatically increase its ability to solve really difficult, complex, multi-step problems. It far outperformed the models that were only trained on the final outcome.
So teaching the AI to show its work, to create a chain of reasoning that's sound at every single point, doesn't hold it back. It actually frees it up to be more competent.
Yes. The value function for truth turns out to be perfectly aligned with the value function for competence. And that is, I think, one of the most optimistic discoveries in AI in the last decade.
It suggests that the path to a powerful AI and the path to a safe AI aren't in conflict.
They're not competing goals. They are synergistic. They might be the very same path.
But let me push back a little here, because the problem of judgment is really subtle. If the value function is just another algorithm assigning a score, couldn't a smart AI learn how to game that system?
How so?
Well, could it learn to produce a beautiful, plausible-looking chain of thought? All the steps look perfectly logical, but it still leads to a secretly harmful or incorrect conclusion just because it knows the PRM rewards things that look like good reasoning.
That is the central ongoing research challenge. It's called robustness against reward hacking, and it's a very real problem.
So what's the defense?
The defense lies in the sheer scale and diversity of the human annotated process data. The PRM can't just be trained to reward, say, the format of mathematical proof. It has to be trained to reward the invariant structures of truth across dozens of different domains: math, code, history, biology, law.
So the more diverse and deeply supervised the data is, the harder it is for the AI to find some universal shortcut to trick the system.
Exactly. The complexity of reality itself becomes our defense against it, gaming the system. The value function has to learn what truth is in a generalized way, not just how to pass a specific kind of test.
Okay, so this isn't just a tool for verification. The value function is the mechanism that enables a whole new kind of reasoning. And to get that, we need to look at the best example we have, the human brain.
Right. Our judgment is deeply tied to our internal evaluators, which we feel as emotions. This is the biological value function. You can think of emotions as a form of compressed evolutionary wisdom.
Ilya Sutskever often brings up neurological case studies to make this point. He talked about the emotionless patient.
He's referring to the classic work of neuroscientist Antonio Damasio, who studied patients with very specific brain damage, usually to the ventromedial prefrontal cortex. The most famous case was a patient he called Elliot.
And Elliot, after his surgery, retained all of his cognitive abilities. His IQ was high, his memory was perfect, his logical reasoning was totally intact.
Totally. He could analyze, he could calculate, he could articulate incredibly complex plans, but in the real world, he was completely inert. He was paralyzed.
Paralyzed by choice.
Paralyzed by choice. Damasio would ask him to schedule his next appointment, and Elliot would spend hours, literally hours, listing the pros and cons of Tuesday at 2 versus Thursday at 3. He'd consider the weather, the traffic, everything. He could analyze forever, but he could not decide.
Because he was missing that internal signal.
He was missing what Damasio called the somatic markers, the gut feeling, the emotional kick that tells a healthy brain, this feels right, or just as importantly, this decision is trivial, don't waste time on it, just move on.
And current AI is that patient.
Current AI is Elliot. Massive intelligence, zero internal confidence or frustration. It doesn't have that internal signal that says, this line of reasoning has a projected value of almost 0. Stop wasting compute cycles on it right now.
And that signal for us, fear, curiosity, even boredom,
Yes.
That's the biological value function.
Absolutely. Evolution has been fine-tuning these functions for millions of years to be hyper-efficient predictors of outcomes. Fear predicts a high probability of death, a huge negative reward. Curiosity predicts a high probability of information gain, a huge positive reward. They are heuristics that let us prune bad choices without having to do a slow, exhaustive calculation.
Okay, so if that's the biological blueprint, how do we build that in silicon? And the key seems to be this idea of reasoning as tree search, which was really perfected by AlphaGo.
AlphaGo gave us the clearest computational model for how to combine that fast System 1 intuition with slow System 2 deliberation. It had a 3-part architecture. First, it had the policy network.
That's the System 1 part, the intuition.
That's the intuition. It would look at a Go board and instantly suggest a handful of the most plausible human-like moves, just like an LLM suggests the most plausible next token.
But then it had the crucial second component, the value network.
And the value network was the value function. It didn't suggest a move. Its job was to look at a hypothetical future board state and just predict the probability of winning the game from that point. It provided that objective judgment score.
And then the third piece, Monte Carlo tree search, or MCTS, was the deliberation engine that used these two things together.
Right. MCTS used the value network to guide its search. And when we apply that same blueprint to language models, we get these more sophisticated reasoning methods like tree of thoughts.
So the AI doesn't just auto-complete a single answer anymore.
No, it simulates multiple potential future paths, multiple thoughts. And the value function, the PRM, is constantly scoring the anticipated value of each of those paths.
But walk me through the efficiency gain here, because simulating lots of paths still sounds computationally expensive.
It is expensive, but it is massively more efficient than a blind linear search. Think of it like exploring a giant maze. If the value function scores a particular path as being very low, say, this line of argument is clearly leading to a logical contradiction, it gets a value of 0.1. The system immediately prunes that entire branch of the search tree.
It just stops thinking about it.
It stops wasting computation on a dead end. It backtracks and explores a more promising branch instead.
And that's the essence of real intelligence. It's that feeling we all have when you're working on a hard problem and you realize 3 steps in, nope, this approach is flawed. You don't keep going for another hour just to prove it. You cut your losses and try something else.
That ability to short-circuit the search space, which is enabled by the value function, is what Sutskever's talking about. It lets the system focus its precious computational resources only on the paths that have a high probability of leading to truth. That's the leap from text generator to reasoning engine.
Which brings us to the more philosophical part of this that we teased at the start. We have to connect this mechanism of judgment to information theory, to the very definition of knowledge and what effective work is.
Right. So let's talk about the difference between knowledge versus information, but using a more geometric, probabilistic framework.
Okay, no math, just the concepts.
Just the concepts. Think of information as this high-entropy ocean of noise. It's the raw, undifferentiated set of all possible states, all the possible moves in a chess game, all the possible words you could say next.
And for a novice, or for a simple AI, the world looks like a uniform distribution, a perfectly flat line.
Exactly. If you have a million possible paths, every single one of them looks equally valid. Or, more accurately, equally likely to be wrong. There's no signal, it's just maximum noise. The landscape is flat, there's no gradient.
And in contrast, knowledge is what?
Knowledge is the specific low entropy vector. It is the single sharp peak in that distribution. It's the one correct answer, the one truth that's buried in all that noise.
So what is the value function doing in this geometric picture?
The value function is the recipe. It's the filter that takes that flat, chaotic, noisy space, and it imposes structure on it. It transforms that uniform distribution into a structured bell curve, a Gaussian distribution, that is centered precisely around that knowledge peak.
I see. So the bell curve represents the probability of success, the peak is the best answer, and the curve slopes down on either side as the answers get worse.
And crucially, that bell curve provides the one thing you need for an efficient search: a slope to climb, a gradient. It tells the agent, go this way. This direction is getting warmer. Your probability of success is increasing. Without that slope, intelligent search is impossible.
And that reframes the entire concept of work.
Completely. If the value function's job is to create the bell curve, then work is the process of minimizing the uncertainty of that bell curve. It's about reducing the spread, the variance.
So let's use the novice versus expert example here.
Okay, a novice might know the general area where the truth is, but their internal bell curve is very wide and flat. High variance means high uncertainty. They know the answer is somewhere in this domain, but they have to check a lot of different possibilities.
Whereas an expert?
An expert, through years of training and developing a finely tuned internal value function, has squeezed that possibility curve into an incredibly sharp, precise peak. Very low variance, very high certainty.
They know exactly which 3 things to check, and they instinctively ignore the million other things that don't matter.
Their value function has filtered all the noise down to just the signal. That sharp, almost vertical peak is the goal. And the work involved is fundamentally about the reduction of entropy. It's not about how much energy you expend. It's about how efficiently you collapse the space of possibilities.
That is a critical distinction. Work isn't effort, it's uncertainty reduction. Okay, now let's talk about the plumbing of how this happens, the mechanics of cognition. Why is the most efficient recipe for success, both in us and in computers, breaking a complex task down into a series of yes-no questions?
Because it is the mathematically fastest way to collapse that uncertainty. A simple binary question, a coin toss, a yes-no, has a possibility space of 2. You need exactly 1 bit of information to resolve it. It is the lowest entropy cut you can possibly make in reality.
And when you stack those simple cuts on top of each other,
you get exponential speed. When you break a big, complex problem into a chain of these binary cuts, each decision you make discards exactly half of the remaining possibility space. So instead of checking n possibilities one by one, which is linear work, you're playing a game of 20 questions with reality.
You're collapsing the space exponentially fast.
Logarithmically fast.
Yeah. And that is the power of true intelligence. The value function isn't just grading the final answer, it's guiding the AI on which specific binary question it should ask next to get the maximum possible reduction in entropy. It's a guide to the fastest path through logical space.
Okay, to really hammer this home, let's look at the 2 absolute extremes of the search landscape. We'll start with case study A, maximum entropy, which is Bitcoin's proof of work. Bitcoin POW is a perfect example of a system where the value function is, by design, intentionally destroyed, annihilated. It leverages a cryptographic property in its hashing algorithm, SHA-256, called the avalanche effect.
The avalanche effect.
Right. What it means is that if you change even a single bit in the input data, the final hash output changes completely in a way that is totally unpredictable. It looks random. This guarantees there is 0 correlation between your input and whether you get a successful output.
So when a miner is searching for the winning number, the nonce, there's no getting warmer signal.
None. 0. Because the probability landscape is perfectly flat, a uniform distribution, the gradient of the value function is 0 everywhere. There is no slope to climb. Your previous guess gives you no information about your next guess. So the search degrades completely into just brute force guessing, a random walk.
Which is why it's so inefficient and costs so much energy.
Precisely. Bitcoin is expensive because it forces this maximum inefficiency. It forces miners to traverse this huge ocean of noise with no map and no compass. There is no value function to shortcut the work. And we have to be clear, this is a feature, not a bug.
Right. That absolute chaos is what makes the blockchain immutable and secure. Its unpredictability is its strength.
Now, contrast that maximum entropy system with case study B, low entropy, like a simple binary system, a light switch.
On or off, a tiny possibility space.
Here, the value function is trivial. It's found instantly. The predictability is almost total. And this is why these simple binary schemes are the fundamental building blocks for solving bigger problems. They are the lowest entropy cuts you can make. They are the bedrock of knowledge acquisition.
So the entire quest for superintelligence isn't just about generating more text. It's about building a system that can efficiently transform complex high-entropy reality, that wide, fuzzy bell curve, into a predictable series of low-entropy binary decisions.
That is a perfect summary of human expertise. An expert is someone whose brain can instantaneously assign a value of 0 to millions of bad paths, so they can focus all their attention on the few promising high-value ones. Their internal value function is so well-tuned that it turns a vast, confusing search space into a steep, narrow peak.
It's pure computational efficiency, achieved through refined judgment.
It's the ultimate evolutionary hack. It's not about being stronger. It's about learning how to ask the right questions in the right order.
This whole journey into the value function, it really has been incredibly inspiring because it takes us beyond just the technical specs and it forces us to look inward, to reflect on what competence and wisdom and reliability actually are.
It does. I mean, Sutskever's focus on process supervision is, at its heart, an attempt to build an AI that can feel the quality of its own thoughts, to algorithmically create something like an artificial conscience that rewards integrity.
And that brings us to the final provocation for you, our listener. If our most important biological emotions, fear, empathy, curiosity, are our guardrails for morality, and they've been imbibed over millions of years of messy trial and error evolution, can we really instill those same ethical constraints in an AI just through algorithmic power, just through process supervision?
That really is the open question, isn't it? Does optimizing an algorithm for logical consistency capture the full, messy, often contradictory complexity of human moral judgment? Or will training this ultimate value function require the collective, explicit effort of the entire human race?
Meaning what?
Meaning we all have to participate in defining and training these ethical boundaries, feeding the model with the best and the worst of our collective history and wisdom.
There's that saying, it takes a village to raise a child. Is that child superintelligence? And are we, through this massive distributed process of feedback and verification that PRMs require, are we the village?
It's a profound thought. And it's what drives our commitment here. We work really hard, iteratively, to make sure that the content in these deep dives is not just surface level, that it's robust, it's thought-provoking, and it's accurate.
We want to bring these conversations to a level where they're truly immersive for the dedicated listeners we have. And we have to stress, this is a community effort. The content we create here is fully open source in spirit because it's built on the sources and the insights that you all share from all over the web.
We rely on that shared knowledge, and we invite you to participate. If you feel like our analysis is even a tiny bit off base, or you have a source that adds crucial context or a counter-argument, please share it in the comments. The ultimate goal here is a symbiosis of artificial and natural intelligence.
We're learning about AI, and in doing so, we're learning so much about ourselves.
Exactly.
And yes, in that spirit of quality, we are always looking for human collaborators, people with deep expertise in these fields, logic, information theory, AI architecture, who might be willing to review and critique our content before we publish it.
We need that human layer of scrutiny to keep this as sharp as it can be.
So if you want to help, please drop a comment or reach out. We'd love to hear from you.
As always, keep searching.
Keep the quest on.